Hi, and welcome to Dr. Jed's Continuing Calculus video series. Today's lesson is section 5.1 from Rogowski, approximating and computing areas. Specifically, we're going to use rectangles for the most part, but areas are not usually rectangles, so we'll have to see how that works. We'll start with the idea, use up something called delta x, which will be a universal width that we're going to use, come up with some specific formulas, apply them, and then kind of look at the limits of those and some abstract notation we can use to sort of compute them or notate them better. So let's first go with the idea. If I want to approximate the area under this curve, so take a look at this curve. It goes from here to here, and we're going to use rectangles to approximate it. Why rectangles? They're easy to use. What's the area of a rectangle? It's the width times the height. This times that gives you the area. Add up all of those, we've got the area of the rectangles. And if the area of the rectangles is pretty close to the area under the curve, it gives you the answer. Well, if it was exactly, that'd be nice. So, how do you find this? There's a lot of issues. The first thing we're going to do is to simplify. We're going to have all of the widths be the same. So look, here the width is that, there's that, there's that, there's that. They're all, this one's thick, that one's thin, so on. We're going to make them all the same for the moment. They don't have to be, not for this theory to work, but for computational purposes it's much nicer. So we're going to call that width delta x. Now how wide is that delta x? Well, if you started at 1 and you went to, well here, start with 1, go to 5. If I want to break that into 2 intervals, well think about that. How long is that? That's 4 long. So what should each of those intervals be if they're the same? It should be, there's 2 intervals, it's half of that. How do you do that? You take this endpoint minus that shows you the width, the total width, divide by the number you want, that'll give you your formula. So let's take a look over here. That's what I say up here. If you want n rectangles between x equals a and x equals b, your width should be b minus a over n. What about height? I'm going to come back here for a second. There are several issues. This first rectangle I drew down here, well actually how did I draw the height? I used the right side of this rectangle to determine how high it goes. I went to the right endpoint, and I went up to how high the function was. The next one I kind of chose like a middle point. The next one, I didn't really think about it, and so forth. So there are several ways to do it. Not thinking about it, not a good choice. But sometimes using the right endpoint would be a good choice. Maybe the middle point would be. Actually, I'm going to show 3 different ways. Rn is determining the height from, is going to be f at the right endpoint of each of the rectangles. Ln, maybe you can see the pattern here. L for the height's going to be equal f at the left endpoint. Mn, M is for the middle. The height's going to be determined at the middle point. You can also do one where it's the inscribed, which means it's below always. The superscribed, which means it's always above there. Those ones are harder to compute because you have to know exactly how tall it ever gets in that range, and that's a whole bunch of issues we don't want to deal with. These 3 are easier. There's one more I'm going to introduce. It's actually not a rectangle. It's not in the book because it's not a rectangle, but it's helpful. It's a trapezoid rule. So if you, instead of drawing rectangles, you drew trapezoids, so you connect the left and the right endpoints and draw like that. It's a better estimate than the left or the right are. And you get it, really, ultimately, just by averaging the left and the right. So actually, I'm going to write this as Ln plus Rn over 2. Now, that's better than the left and the right. The midpoint is also generally better than the left and the right because it's right in the middle. How does this work? Let's do an example. Let's take an example, a function that's not particularly hard to do. So, f of x equals x squared plus 1. We're going to start at x equals 1, go to x equals 2 with 2 intervals, 2 sub-intervals. So first off, before we even do anything, I'll erase this graph actually, and we'll start over. We're going to have this graph that goes like this. 1 there, 2 there, and I want to go halfway in between. What is halfway in between? Well, hopefully you can see that's 1.5. How wide are these things? Well, you don't really need any formula to tell. That's 0.5 wide, that's 0.5 wide, but formally it's b minus a over n. That's how wide they are. Now, what are the rectangles? Let's do Rn first. Rn says, for each of these rectangles, I'm going to draw the rectangle that's as high as the endpoint here, on the right. So from that rectangle, it goes to 1.5, that's the right side. Here it's 2, go to the right side. Notice this is an overestimate, because there's stuff above the whole area we want. How do you find that? Width times height. So it's going to be 1/2, that's the width. Why is that the width? Because that's the delta x. Times the height, that's f of the endpoint. Width times height. The height is the right endpoint of this interval, so that's 2. F of 2. Now notice, I'll compute that out right now, because we've got 1/2 here, 1/2 here. Sometimes you just pull that 1/2, which is the delta x, out. Then you've got f of 1.5, plug it in here, get 3.25. Plug 2 in here, you get 5. You end up with 8.25. Divide by 2, so 4.125. That's too much. The area is less than that. How do I know? Look at these rectangles. They're bigger than the interval. So now let's do the L's. The L's will be better in some ways. They'll be smaller. Because we go, the left side is the height. The left side of this interval is 1. Well, so the height is determined by f of 1. The height of the second one, well, it's determined by the left endpoint of that, 1.5. So that's some work to do, but notice there's overlap in our work here. Why? Because the left endpoint, the right endpoint's in the middle of the same things. The left endpoint, the right endpoint of this interval is the same as the left endpoint of this interval. So if you have enough of them, just compute for the rights. The lefts are going to be the same, except they're going to differ with one piece difference. What's the value? Plug a 1 in here. Most of these, the 3.25, that's the same. That was easy to do. 5.25, so 2 point, is that right? So 4, so 2.625. The middles are harder to do. So notice though, the right's too big. The middle, the left's too small. What about the middles? Well, we have to go in between. The middle of this first interval, that's 1.25. So we go up to here. What about here? That's 1.75. So we go to there. Hopefully you can see there's a little bit too much here, a little bit too little there. They help balance out a little bit. A little bit too much here, a little bit too little there. Maybe it balances. It should be a better estimate in any case. What do we have? We're going to have 1/2 of f of 1.25 plus 1/2 of f of 1.75. Now notice, those are not going to be like these ones because we're using different points. You compute it out, still it's going to be 1/2 of something. We get 3.3125, which is a way better estimate. And then the t. The t is simply take the two of those we had from the first, the right and the left, divide by 2, and you get 3.375. Notice these two are pretty close. The real answer is probably right about 3.3 something. These two are a bit off. Now how could you make it better? You could put more intervals. If you put more intervals, you have better rectangles. Let's do now one with 4 rectangles. Cosine. It introduces a new idea, because if I want rectangles to cover this is, the rectangles here, the heights are positive. What are the heights over here? They're negative. This method of using the heights determines something not called area, but called signed area. Signed area is actually the thing we want. If you really want true area, just put absolute values and you're fine. But we're going to use from 0 to pi on the cosine function, just like that. Now, hopefully, symmetry can tell you something here. How much area is there? How much area is there? If I'm calling this negative, I'm calling this positive, those are the same shapes. the signed area should be 0. A little bit of logic can tell us that, and that would tell us faster than this. But we should still compute this. Delta x, this could be your b minus your a over your n pi over 4. So your L, I'm going to do this fast just because I want to show it off. So the left side of each of the rectangles, the height here is 1, because that's cosine of 0. The height of this one, well, that's pi over 4. What's the cosine of pi over 4? Think back. Square root of 2 over 2. It actually doesn't really matter, because we'll see in a second. How about right here? This is kind of weird. The height is 0. What's a rectangle with a height of 0? It's nothing. There's no height, so there's no area. And over here, this is 3 pi over 4. You may not remember that, but look, that's positive, that's negative. They're the same place on the graph. That's negative square root of 2 over 2. So you get pi over 4 for that one. The right one doesn't have this first bit, does have an end bit. So it doesn't have the 1, it does have a minus 1. Think about it. It doesn't have this, but it'll have a minus 1 in there. You're going to get minus pi over 4. Now, in this case, if you did the midpoint rule, or if you did the trapezoid rule, you would get 0, and they're both a better estimate. But if I did L8, or I did R8, or I did L16, or 32, or 155, I'm going to get better estimates. Which leads to the fact that the true area, these methods, Rn, Ln, Mn, and Tn, all of them, if n gets big enough, converge on the true area. Unfortunately, limits require a notation, a formal notation. So the rest of this section is about writing up a notation. So what is Rn? It's the sum of all of these. Why? Because this is A plus how many endpoints you moved over. How many sub-interval endpoints you moved over. We need something for sum of. That's not a word we have yet. So this right here means sum of. There's the delta x, there's that. What does this mean? It means we do this when I is 1, we do this when I is 2, we do this when I is 3, and so on until we get to that number. This is called summation notation. It's awkward, it's a little funny. It's more precise than writing words like add these together or sum of. It's formal. And there are a lot of rules. There are rules on page 289 of the book. There are rules on page 292. These rules are useful for computing sums that are just formal sums. Here's an example. If I add numbers from 1 to n, like that, 1 plus 2 plus 3 plus 4, all the way up to, say, n. If n is 15 or 25 or whatever, I get that formula. Why? It just works. Let's use that. If I went, say, from 1 to 6 here, we'll get the 2 out of there. So, with an I there, 1 to 6. Well, that formula says it's going to be 6 times 7 over 2, which is 21. That's how I'm using the formula. How about if I do it with a smaller area? I goes from that area, region, whatever you want to call it. How about I put a 3i in there? Well, that's got a 3, and we have to figure out what to do. The 3 can be pulled out, but this doesn't start at 1, so it's a little bit more awkward. It may be more illustrative, that's a fancy word, by plugging each of these in. This is saying do it with 3, do it with 4, do it with 5, and do it with 6. And add those together. That's what you get. There are other ways to do this that are fancy, but this works. Try it all out, and hopefully it'll make a lot of sense. This is Dr. Judd.